So first, let us start with flux. What is the definition of flux? So flux is quantity per area per time. Any quantity from a unit area per unit time uh, is known as flux. Majorly, there are two types of flux. First is molecular flux. Secondly, convective flux. Molecular flux is diffusivity into gradient of quantity by volume. And convective flux depends on the velocity of the quantity that we are looking at. And in convective flux, mostly there is movement of the molecules. That's why a characteristic velocity is related to convective flux. So convective flux is equal to quantity by volume into characteristic velocity. Adding both the fluxes, we get total flux. That is total flux. Now here we can modify our formula a little bit. It is transport property into gradient of driving force, which is now written as diffusivity into gradient of quantity by volume. Secondly, convective flux is quantity by volume into characteristic velocity, which can be written as quantity into characteristic velocity. It remains same. There is a little bit change in molecular flux, so that we get the term of diffusivity. Now let us look into interphase flux that we are going to discuss today. Interphase flux. In interphase flux, basically there are two phases, phase one, phase two, and in from both the phases there is transport of flux. So in the interphase, we are going to discuss about the total flux on the interface. And interface flux is equal to the formula which we had discussed earlier. Our topic for now, our focus for now is interface flux in heat transfer. The flux can be in anything. It can be flux for heat transfer, flux for mass transfer, flux for momentum transfer. But for now, we are looking into flux, interface flux in heat transfer. So let us consider a plate of length L and temperature TW. Now, above it, there is a uniform stream of air that is flowing with velocity V infinity and temperature T infinity. The axes are represented here, y-axis and x-axis. So this is the formula that we discussed earlier. So interface flux, that is the total flux at the interface, is equal to diffusivity, gradient of quantity by volume into characteristic velocity. So here we write Ey at y is equal to 0, because according to the axis it is y is equal to 0, is equal to Qy plus rho Cpt Py at y is equal to 0. The second term is for convective flux, the first term is for molecular flux. Both has limit at y is equal to 0. Now, if we look closely, we'll again go back to the, yeah. So here, if you look closely, the first layer above the plate at the of length L, first layer would have zero velocity. This is our assumption, and it is a condition that we can see also, because the first plate would feel the friction from the plate. So that's why we consider the layer of air which will be just above the plate will experience some force, and it will not have the velocity which the upper layers of air have. So that's why, according to no slip condition, there is no slip. That is, relative velocity at the interface is zero. That's why we consider the first layer velocity to be zero. Now at y is equal to zero, Vy will become zero, and we will neglect the convective flux term. That is this one. There is That's why, for due to no slip condition, no slip boundary condition, the Vy becomes zero and the whole convective flux term becomes zero. Now the total interface flux is equal to molecular flux at y is equal to 0, that is at the interface. Now we know Qw is equal to minus K del T by del Y. This is our Fourier's law. Now integrating rate of heat transfer is equal to the total rate of heat transfer is equal to, we'll multiply it by, we will integrate the whole equation of flux over area. That will give us the rate of heat transfer, because what we had discussed is heat per area per time would be flux. Now, if we multiply flux with the total area, we'll get heat per time, that is rate of heat transfer. So we'll integrate over x-axis and y-axis for 0 to L and 0 to W. Not y-axis, will z-axis, because the plate is in this plane. So we'll integrate it over x and z-axis from 0 to L, from 0 to W. These are this is our equation for flux. Now, when we write the equation, this QW has the term dou T by dou Y. What is this? This is a differential equation at the interface of both the phases. Now let us look what is happening at the interface. Temperature gradient at the wall in presence of flow. So there is a flow of air, and at that interface, we have to find the differential of T. That is how T is varying over the axis of Y. But this is what is happening. Now we can see that at the interface, it is very complex. The flow is very complex. We cannot determine how the air is behaving, how the temperature is varying at the interface. This is called complex nature of flow characteristics. So we cannot exactly determine the flow characteristics. Due to this complex nature, this is where we are limited. We cannot define this, we cannot analytically define this. We don't have an equation to write that dou T by dou Y is a function of this, is a function of Y. We cannot write that because it is such a complex flow. So what we will do, we will use, it is difficult to determine it analytically. So we will do some experiments. So with lot of experiment, it has been concluded this equation, that is Newton's law of cooling for convection. So QW is equal to H into TW minus T infinity. This is a experimental conclusion, not analytical. So we will use this equation to move forward in our calculation for rate of heat transfer. So using this Newton's law of cooling, combining equation 3 and 4, we get the equation. We take out TW minus T infinity, integrate it over 0 to W and 0 to L, that we would make. Now here a term is introduced, that is H. We'll discuss it about later. Now after integration, there is W, there is L, H integrated, and TW minus T infinity. Now what is H? H is actually the heat transfer coefficient, HTC, heat transfer coefficient. What is heat transfer coefficient? Heat transfer coefficient is introduced because we are discussing about interface. And what happens at interface? In interface, there is complex nature of flow characteristics. Due to this complex nature of flow, we are unable to define the flow, unable to define the variation of temperature. That's why we require H. With K, we cannot move forward. This equation, that is equation number 3, we cannot move forward. That's why we need another term, that is transfer coefficient. With the help of this transfer coefficient, we will move forward. So that is H, which has been introduced using Newton's law of cooling. So now, after integration, it is average H. What is average H? H integrated over the length, or H integrated over the area divided by area. That is H dot dx dot dz integrated over the area divided by the area. This gives us the average H over the flat plate. This equation gives us this. Okay. So now, with the help of Newton's law of cooling, we have got the equation for rate of heat transfer. Combining equation 1 and 6, then rearranging from equation 1 and 6, we get the equation, generalized equation for rate of heat transfer. That is Q is equal to AH into H into delta T characteristics. What is delta T characteristics? If we go back in our slide, we'll see TW minus T infinity. This is our characteristic delta T. So since we are writing this whole term as delta T, why have we written characteristics? Because it depends on the flow, on the system which we are looking at. Area is the cross-sectional area, or the not the cross-sectional area, the area over which heat transfer is occurring. Delta T characteristics temperature difference. Now let us discuss about this characteristic temperature difference. So in this equation, we know about we know about AH, that is the area over which heat transfer is occurring. H is the heat transfer coefficient, and here we are writing average heat transfer coefficient, which has the formula this. Now we are looking at delta TCH, that is characteristics temperature difference. Now characteristic temperature difference can be different for different systems. It is basically the temperature minus temperature at any point minus the bulk temperature. Now bulk temperature may vary. How? If you look, for example, if you are looking at flow through a pipe. So flow through a pipe, if there is, for example, there is a double pipe, there is heat exchange happening. So at the axis of the pipe, the center line axis of the pipe, this distribution shows us axis of the pipe will have the maximum temperature, and that temperature will become the bulk temperature. So here in delta T, it will become T axis minus T. So earlier, if we are looking at flat plate, we will see the T infinity represent the temperature at a distance infinity. That is y is equal to infinity. See this. This is T infinity. At y is equal to infinity, we get the temperature T infinity, and this is the temperature which we are going to use in characteristic temperature. But it is not the case when we are looking at flow through pipe. Here, the temperature that we would subtract it from is the temperature at the central line. So this defines the characteristic temperature. Therefore, it is known as characteristic temperature because it is different for different system. It depends upon the character of the system. Now, heat transfer coefficient. It tells us about how efficient is the heat transfer. It depends on many properties. Thermal properties of the medium, specific heat transfer coefficient, now how the fluid flows, whether it is laminar flow, whether it is turbulent flow. Turbulent flow enhances the transfer. Surface characteristics, roughness, fouling. Okay. So now we have discussed about heat transfer coefficient. So now till now we have defined heat transfer coefficient and on what factors it depends. Now let us look at the physical significance of heat transfer coefficient. So we have in total we have used two laws. That is, first is Fourier's law of conduction. Second is Newton's law of cooling. Now Newton's law of cooling was used because we stuck on the part of dou T by dou Y. So analytically we didn't have any equation to define that. That's why we used Newton's law of cooling, which is experimentally proved. Combining these two equations and rearranging, we get the term heat transfer coefficient H is equal to minus K divided by TW minus T infinity dou T by dou Y at Y is equal to 0. That is at the interface. Now this is the actual case. This is what actually happens at the interface. The distribution is like this. Now we have got to the equation of heat transfer coefficient. That is equation number 3. So let us look into the actual case. What happens? The actual temperature distribution. Now let us look at this graph carefully. So there is the y-axis represents the length. Y-axis represents the distance from the wall, and x-axis represents the temperature. So at y is equal to 0, that is at the interface, the temperature at the wall, at y is equal to 0, it is the surface is it is the surface of wall, that is temperature Tw. As we go up, the temperature changes, and at t is equal to infinity, that is when we go from infinite distance from the plate, and this is the temperature of the air at infinite distance from the plate, that is T infinity. So this is the temperature distribution curve. Again, what are the axes? Y represents the length and X represents the temperature. So this is the equation that we get. H is equal to minus K divided by Tw minus T infinity dou T by dou Y. So this is, now we are looking at the distribution of the temperature. This is the actual case. What happens over the length L? The temperature is distribution. Temperature is like distribution is like this: Tw and T infinity over here. So this is the actual case. But for the physical significance, let us devise an ideal case where we consider that there is a film of thickness delta, and there the distribution is linear, that is dou t by dou y is equal to slope, some constant. So we are assuming that the distribution at the interface is linear distribution, and there is a film thickness of delta t, that is here. This is the ideal case. Actual case is this. Ideal case is this straight line temperature distribution. Total actual resistance is equal to uh, or is equivalent to resistance of the stagnant film of thickness del T. So we are assuming that at the interface, or at the interface there is a film, stagnant film of thickness delta T that has some resistance. That resistance is equal to total actual resistance. So this thing actually comes, we have derived this thing actually from the film theory. In film theory, we have studied there are different, three film theories. In stagnant film theory, we have learned that there is a stagnant film, it has a resistance. This gives us the physical significance. So this is the idealized case that we are discussing about. Tw is at the wall, and at a distance of delta t, stagnant film thickness delta t, there is the temperature T infinity, and there is a linear distribution. The equation dou T by dou Y at Y is equal to 0 is equal to T infinity minus Tw. It increases divided by dou T. This gives us the quantity dou T by dou Y. Now rearranging the equations, that is Q is equal to minus, this is Fourier's law, this is Newton's law of cooling. Rearranging, we got the equation for H. Now we have defined dou T by dou Y, that is the slope, as T infinity minus Tw by dou T. Combining the equations, we get H is equal to K by delta T. That is, heat transfer coefficient is equal to thermal conductivity upon dou T. Dou T, what is dou T? Dou T is the stagnant film thickness. We are assuming in ideal case there is a stagnant film of thickness delta T. With the help of this thickness, we are giving a significance to heat transfer coefficient, because thermal, we know thermal conductivity of anything. Thermal conductivity is a property of material, so we know about it. But H is a property of system. So to give a physical significance to property of system, delta T, so dou T is delta T is used. That is the stagnant film thickness. Film heat transfer coefficient. So after completing our discussion on physical interpretation of heat transfer coefficient, let us dive into an example. So this is a very good example. Energy generation rate per unit volume as a result of fission within a spherical reactor of radius r is given as a function. So here we can see the generation of energy per unit volume is given, where r is the radial distance from the center. Cooling fluid at a temperature of T infinity flows over the reactor. So there is a cooling medium, cooling fluid which is flowing over the sphere. If average heat transfer coefficient is given, determine the surface temperature of the reactor. Okay. So what can we understand from this? So if you look at the diagram, here there is reaction occurring. Due to this, there is energy generation at the surface of the sphere or at the surface of the reactor. Heat is being transported, or it is being transported by convection, and inside there would be generation. This heat generated is going out of the reactor. How? The heat is being extracted by the cooling medium by convection. The outer fluid is different. So there is an interface at the reactor surface where heat transfer is occurring. Now here is the solution of this question. This is what we discussed. Rate of energy out by convection is equal to rate of energy generation inside the sphere due to fission reaction. The rate at which energy leaves the sphere can be given by Newton's law of cooling, which we learned previously. So it is area into average heat transfer coefficient into delta T characteristics. So here characteristic temperature would be the temperature of the cooling fluid that is flowing, and TW would be the surface of the temperature of the surface which we require. So here we have got the equation for rate of energy out. Now we will go for rate of energy generation. So here the solution is using spherical coordinates where r, theta, and phi is used. So it is integrated over the spherical volume by taking a differential element. We integrate it over 0 to 2 pi theta, 0 to pi phi, and 0 to r radius. So by solving this, we get the equation number 3. Equating these two equations, equation 2 and equation 3, we get our desired profile of surface temperature. Now we can do, or we can solve this question in using Cartesian coordinate also. So we are looking at this sphere. Let us take a differential spherical element at a radius of r. So the volumetric energy generation is given as a function of r, that is E is equal to E naught into 1 minus r by r whole square. So rate of energy out is equal to rate of energy generated. Using Cartesian coordinates, because heat transfer is not vector quantity, we can use Cartesian coordinates here. So rate energy out is equal to the volume of that differential shell, 4 pi r square into this is the rate of energy out, that is by convection. Therefore, it is area of the outer surface, that is 4 pi r square, into h, that is average heat transfer coefficient, into delta T characteristics, that is TW minus T infinity. That is the first equation. Now we will calculate the heat generated. So let us look into heat generated. Heat generated is equal to integration of E dot dV, that is the energy generation per differential volume integrated over 0 to r. Here, let us assume the distance differential shell is at r distance with thickness dr. So this is the term for energy generation per volume. Now we will multiply it by volume term. That's 4 pi r square dot dr. This is giving us the volume of differential sphere. And we will integrate it over 0 to r. Integrating it and substituting the limits, we get the equation, which is similar to what we got using spherical coordinates. And equating it with equation 1, we get our desired temperature equation, that is surface of the reactor. So here we complete our example solution.
Okay. So now our next topic is interface in mass transfer. So basically we will now go term by term. The first term here is interface flux, which we discussed earlier in the heat transfer. Now mass transfer. So what is the first basic thing which we think of when we think of mass transfer? It is the osmosis field, of course. The resin, when it is dipped in water, after some time the resins get like swollen. This is basically because of the mass transfer. And at that time we didn't know that that is an interphase mass transfer, but now we can differentiate it. So what happened? The higher water concentration in the outside bowl, and this is the resin part. So there was a higher concentration of water here, and thus it moved from higher to a lower water concentration. Okay, so this is the basic principle of your mass transfer. And this DNA type structure in the between is what we can refer to as the interface. This part we can refer to as interface. Now, the next question is, what is the driving force for mass transfer? It seems to be a very silly question to ask, right? But to be honest, there is some facts which we actually don't know about the driving force. In heat transfer, when we consider an equilibrium, it is very simple that if the both the phases have same temperature, then we consider it to be an equilibrium. But this situation is not necessarily true in mass transfer. Even if both the phases have same concentration, it is not necessarily that they both are in equilibrium. So, the actual definition of driving force for a mass transfer is not merely just concentration difference, but actually the chemical potential. Both concentration difference and chemical potential are the driving force of mass transfer. Now we will see some concentration profile. Okay. Here we will assume that wait, wait. Here we will assume the left side of the interface as one phase and the right side of the interface as the second phase. Okay, so this is the bulk part of phase 1, this is interface of phase 1, this is interface of phase 2, and this is the bulk part of phase 2. Now the solute will move from the bulk of phase 1 to interface of phase 1, and from the interface of phase 2 to interface of to the bulk of phase 2. Now, this is the straight line is to, like, ideally, if we think of any difference, this is the ideal way, or according to the film theory, this is the ideal case of the concentration profile happening in the film across the interface. But in the actual case, there is a curvature or a parabola in which there is the concentration profile, which we will study later in the physical significance part. Now consider that the phase 1 has the mass transfer coefficient range of kx, and phase 2 has the coefficient of ky. Now, if we consider the basic rate of mass transfer equation, which is kx into the concentration difference of phase 1, like ya1 minus yai, the bulk concentration minus the interface concentration, which is equal to mass transfer coefficient of phase 2 into yb1 minus ybi, like the bulk concentration of phase 2 minus interface concentration of phase 2. Okay, so this is the equation. But what do you think is the problem here? The problem is that yai or ybi, the interface concentration cannot be practically determined. So for that, this is the interface. So this concentration cannot be practically determined. So for that, we came up with the term of overall mass transfer coefficient, which is denoted as capital Kx, capital Ky. This x and y suffix is used so that with which phase context the mass transfer equation needs to be defined is the purpose for that suffix x and y. Okay, now to simplify the things or to quantify the things, we will consider one situation. We will consider the flow over flat plate. Okay, so consider this is a flat plate which is coated with some species A with the concentration of CaW. Okay, now there is a uniform stream of air which consists of species B with velocity V infinity and concentration of species A as Ca infinity. Okay. Now the species A, which is coated on the flat plate, is diffused into the uniform stream of air with concentration of Ca infinity. So this transfer of molecules is NaW. We will consider that flux, mass flux will be denoted as NaW. Okay, so this is the setup for which we are going to quantify the things now. So, rate of mass transfer from plate surface. What do you mean by rate? Rate in the simple terms is flux into area, correct? Which is quantity per unit time. Okay. Now, we will write this in the mathematical terms. This NaW, as we discussed it earlier, is the mass flux. And this is dx dz, which is your mass transfer area. The area which is concerned for the mass transfer happening in this situation. Okay. And Na dot is the mass transfer rate. Okay. Now, as we are considering the interface flux, so our area of concern is the surface, for which is y is equal to 0. So, as we discussed it earlier, interface flux is the total flux at interface. This first term, diffusivity into gradient of quantity by volume, is your molecular flux. Okay, and quantity by volume into characteristic velocity is your convective flux, because there is a term of velocity. If there is a term of velocity, then that is always associated with the convective flux. And all this is happening at the interface. Now, as we saw in the equation 2, NaW is written as NaY at y is equal to 0. Okay. This diffusivity is DAB. Gradient of quantity by volume is dCA by dy. Now, there is a term of negation. This negative sign comes because quantity by volume is decreasing as we are moving forward with y. So that's why there is a minus sign there. Plus, quantity by volume is your Ca into Vy. Vy is your characteristic velocity. Now, what is this Vy? We will see. Vy is basic formula is Ca into Vay plus Cb into Vby upon C. Now, we will configure what this formula actually is. Okay, see the terms. Split the terms denominator, it will come as Ca upon C into Vay. Okay, now Ca upon C, concentration is basically your moles upon volume. Okay, number of moles upon volume. Now, since the volume is same, so we can cancel out the volume. So basically, the ratio of your Ca to C is equal to your number of moles of A upon total number of moles, which is your mole fraction. The basic definition of an average velocity is your number of mole fraction into velocity of A plus mole fraction of B into velocity of B. This is the very same definition. It's just that the number of moles or mole fraction is expressed in terms of concentration. Okay. Now we will, to simplify our calculations, we normally consider the no slip boundary condition. The no slip, what is the, now we'll see what is the no slip boundary condition. Basically, when over us there is a solid and a fluid interface, we consider that the relative velocity of the fluid and the solid is same, so the overall velocity turns out to be 0. But in this case, now we can, in solid and liquid there are different component, multiple components involved. So what we can see is that at y is equal to 0, like at the surface of the solid plate, there is no species B. If there is no species B, there will be no velocity. So that will be 0. Okay. But that does not mean that your Vay is 0. So the Vy terms is a non-zero term. But according to the no-slip boundary condition, we need that term to be cancelled out. So we will make some assumption. We will assume that there is a low mass transfer. Okay, that the amount of A which is diffusing from the solid plate to the fluid is less. So what will happen, that the Va term, Vay term is also 0, Vby term is also 0. So Vy term, Vy star is also 0. So the second term here gets cancelled. And we are left with only this dAB into dCA by dy at y is equal to 0. Now we will substitute this term into equation number 1. But this dCA by dy at y is equal to 0 is difficult to determine practically. dCA by dy is your quantity by volume. This Ca is cannot be practically determined at the interface. So for that we need to replace this term. So there comes the Slattery equation, or which we commonly call as Newton's law of mass transfer. This is very similar. How did the Newton law of cooling came into place? This is a very same context here. So the Slattery equation states that the mass or molar flux is equal to Kc into CaW minus Ca infinity. Now Kc is your mass transfer coefficient, and CaW is your concentration of species A at wall minus concentration of species in bulk, Ca infinity. Okay, this is a Slattery equation. So instead of putting this equation, because this is difficult to determine, we will put this equation in equation number 1. So 1 and 5, we get this integration. Now, since CaW and Ca infinity are constant and is not changing with respect to area, we can take these terms out. Okay, so the remaining terms are Kc into dx into dz. Now dx dz integrated over W and L will give you WL into CaW minus C infinity. Now there is this term with a bracket Kc. This is called as the average mass transfer coefficient, which is the local mass transfer coefficient multiplied by the mass transfer area upon total area. Okay, this total area is WL into integration of Kc into dx dz. This can be termed as your average mass transfer coefficient. So now we will this equation number 6 and 8. Okay, so WL is replaced by the term AM, which we call as mass transfer area. Kc is the average mass transfer coefficient, and CaW minus Ca infinity is written as delta Ca characteristic. This delta CaCH is the characteristic concentration difference. Why the word characteristic came here is because we are generalizing the equation. This setup we considered to quantify was a flow over a flat plate. But consider if there is a flow over a tube. At that time the CaW will remain same. The wall of the pipe will be your CaW, but the definition of a bulk changes for the flow through a pipe. At that case, the concentration which is at the center axis of the pipe will be considered as your bulk concentration. So that's why rather than writing it as a concentration difference, we wrote the term as characteristic concentration difference, which is defined according to the system which we are considering. Okay, now we will study some more about mass transfer coefficient. Basically, the basic objective of a mass transfer coefficient is how efficient is the mass transfer. So it depends on many factors like fluid properties like density, viscosity, diffusion coefficient. Okay, this diffusion coefficient, how the mass transfer coefficient depends on the diffusion coefficient, we will study in some further slides. It also depends on the fluid flow, whether the flow is laminar or a turbulence. The most practical application which I can share about this turbulent flow is of the heat exchanger. In a heat exchanger, we normally put out some baffles. The baffles restricts the laminar flow of the fluid, thus creating a turbulence. This turbulence helps in efficient mixing and thus efficient mass transfer. Therefore, we can conclude from this example that the turbulent flow enhances the mass transfer, which enhances your mass transfer coefficient. The third property on which it depends is your geometry. Like what is the surface area? Surface area, now here the surface area term is very vague. Here the term should be what is the concerned area at which the mass transfer is occurring, and temperature and pressure. These like if temperature increases, diffusion coefficient increases. But according to the film theory, mass transfer coefficient is inversely proportional to your diffusion coefficient. So if diffusion coefficient increases, your mass transfer coefficient decreases, which basically turns out your mass transfer decreases. Okay, and if there is a higher pressure, then your boundary layer increases, and your resistance decreases. So that will enhance your mass transfer, right? Okay, so these are the properties on which mass transfer coefficient depends. But if we have to consider, like, practically picturize what exactly is a mass transfer coefficient, so we will see the physical interpretation of mass transfer coefficient. Now, this equation number 4 is NAW is minus DAB into DCA by DY. This is commonly called as your Fick's first law of diffusion. And the equation number 5 is your NAW is Kc into CAW minus CA infinity. This is what we studied now. It is called as your Slattery equation. Now, since both are the flux, what if we equate both of them combined? So, Kc into this will be equal to minus DAB into DCA by dy at y is equal to 0. Okay, we will put only the coefficient of the left hand side because we need to have the relation between Kc and your DAB. Okay, so now this is the equation which we are studying. Okay, so this dCA by dy at y is equal to 0 can be considered as Ca infinity minus CAW upon. Okay. I will explain it using this diagram. This is the idealized case. This is the graph of a concentration profile which can be made by assuming that film theory is applicable here. So, at the bulk, the concentration is Ca infinity, and at the wall, it is CAW. So, the slope of this line will be dCA by dy, correct? And this film has a thickness of delta C. So the slope can be written as delta CA, dCA upon dy can be written as dCA by dy. It can be written as Ca infinity minus CAW upon your film thickness, which is delta C by the basic definition of slope. Okay, so substitute this equation number 10 in equation number 9. Okay, so CAW minus CA infinity and CA infinity minus CAW. This terms gets cancelled and minus minus will give you plus. Okay. And so Kc. So combining the whole equations, we get Kc is equal to DAB upon delta C, where your delta C is the film thickness. Okay. So from this relation, what we understand is mass transfer coefficient is directly proportional to your diffusion coefficient and is inversely proportional to your film thickness. So if the thickness decreases, so your mass transfer coefficient increases. If the film thickness increases, your mass transfer coefficient decreases. This is the physical interpretation of a mass transfer coefficient. Now we saw a few terms here, CAW, and okay, so this CAW depends on whether the fluid, on the nature of the fluid. If the fluid is a gas, we can assume that it is an ideal gas behavior, and we can use the ideal gas law, which is PV is equal to nRT, and we can get the concentration as PA saturation upon RT. But if the fluid is a liquid, then we will consider the concentration at the wall as the solubility of solid in liquid at TW. This solubility of solid and liquid at TW can be correlated with the Henry's law, which is used for interphase mass flux. Okay, and okay, so here we saw the term of PA saturation. Now, how will we calculate this PA saturation? So, to calculate this PA, we can use the Antoine equation. The generalized format of this is ln P saturation is equal to A minus B upon temperature in Kelvin plus C. These A, B, C are called as Antoine constants, which are specified from system to system or material to material. And using this format of equation, we can determine the P saturation, where P saturation is in mmHg and T is in degree Kelvin. Okay. To analyze the rate equation which we studied right now, let's solve some numerical and understand it more better. Okay, so the numerical is 0.5 liter of ethanol is poured in a cylinder tank of 2 liter capacity and the top is quickly sealed. The total height of the cylinder is 1 meter. Calculate the mass transfer coefficient if the ethanol concentration in the air reaches 2% of its saturation value in 5 minutes. The cylinder temperature is kept constant at 20 degrees Celsius. The physical properties for the solute ethanol at 20 degrees Celsius is given: the density, its molecular mass, and P saturation. Now, since we are assuming that ethanol is present in the form of gas, we can assume the ideal gas behavior. Okay, so before starting the numerical, we will first understand what is our setup. Okay, now this is a cylinder of 2 liter capacity, and some 0.5 liter ethanol is trapped inside the cylinder and it is quickly sealed. Now, after 5 minutes, 2% of the concentration of ethanol which is trapped is diffused into the remaining part of the cylinder. Okay, so now this is our setup. Now we will start with the calculation part. So the first thing which we see here is the 2% of concentration is diffused. Okay, so first, I think we should calculate what is the concentration which is present here in the 0.5 liter of ethanol. The concentration is not given. So we will calculate that first. The P saturation value is given as 43.6 mmHg. Now we need to convert this into the standardized units. So 43.6 by 760 atm, because 1 atm is 760 mmHg. And the R, which is the universal gas constant, is 0.08205 liter. Now, since the volume of the cylinder is given in liters, so that's why we are considering this value of R. And the temperature is given in degree Celsius. So we will convert it into degree Kelvin. Now, as discussed earlier, the fluid which we used is a gas. So we will assume ideal gas behavior. What is the ideal gas law? It is PV is equal to nRT. Now, N, what is your concentration? It is your number of moles upon your volume. So, in this ideal gas law, which is PV is equal to nRT, N by V is equal to P by RT, which is your concentration. Correct? So, the CAW will be PA saturation upon RT. Now, put these values which we calculated at the top in the equation, and we get the concentration of the ethanol which is trapped here at the bottom of the cylindrical tank. Okay. Now, the second point which is mentioned in the question is that from that 0.5 liter of ethanol, 2% of its concentration is diffused into the remaining part of the cylinder with the time of 5 minutes, within the time period of 5 minutes. Okay. Now, here two things are important. First, we calculated this concentration 0.02, like 2% of this concentration is diffused. So we will calculate the number of moles which are diffused. Okay. Now, since this cylinder is of 2 liter and ethanol trapped is of 0.5 liter, so the remaining part will be the volume in which the 2% is diffused. So we will consider 2 minus 0.5, it is 1.5 liter. Now, since the concentration is in meter cube, kilomole per meter cube, we will convert this liter into meter cube. Okay, so number of moles will be 2% of the concentration into the volume, because concentration is number of moles upon volume. So number of moles will be concentration into volume. So this will be 7.17 into 10 to the power minus 8 kilomoles. Okay, now we will calculate. Now, okay, now we got number of moles, but how will we get the mass transfer coefficient related to that? Now, mass transfer coefficient is in some relation with flux, right? But we don't have the mass transfer coefficient. If we were to use the Slattery equation, Okay, so we will go by the basic definition of flux, which is quantity per area into time. This is the basic definition of flux. Now, since this is a molar flux, so the quantity here will be number of moles upon area into time. Okay, the number of moles which we calculated in the earlier slide upon area. Now, area, this is a cylinder. Okay, so the volume upon the height of the cylinder will give you the area. Okay, as mentioned in the question, the height of the tank was 1 meter and the volume is 2 liter. 2 liter is 2 into 10 to the power minus 3 meter cube upon 1. So that will give you the area. And as mentioned, the 2% of the concentration is diffused in 5 minutes. Now, since it is in minutes and we need it in seconds, it's 5 into 60. So, 1.2 into 10 to the power minus 7 kilomole per meter square second is the flux which we need. Now, by Slattery equation, molar flux is your mass transfer coefficient into concentration difference. Correct? Now, in this, the left hand side, NaW, we have that value. Kc, we have to find. CaW, we have calculated. And now the question is Ca infinity. Now, what is Ca infinity? Ca infinity is the bulk concentration of species A. Okay. Now, here in the cylinder, this 0.5 liter ethanol is trapped and 1.5 liter is empty. And this ethanol is being diffused in this 1.5 liter. So this remaining 1.5 liter part is your bulk of the system. Now, since initially there was no ethanol present in that 1.5 liter part, so we can say that the bulk concentration Ca infinity is 0. Okay. So the molar flux is equal to Kc into Caw. Okay. Now, here we got the value of NaW and we have the value of Caw which we calculated earlier. So by putting the values of NaW, we can get the value of Kc. So this is how we can use the concept of Slattery equation and the basic definition of flux to solve any numericals based on the interface flux of mass transfer.